He's married, Raoul?
Yes,
Again?
he's married for the second one.
Second, has a family, has children?
No, he has no children, unfortunately.
Oh. Mm-hmm.
Okay.
Just a moment.
Anytime you like.
Please.
Yeah.
Well,
Okay, good. Yes? Yes?
Yes.
Yep, thank you.
shall we start?
I'm ready. Yeah.
Well, let me start now. Do you hear now? Okay. It's an honor and a pleasure to introduce Professor Michael Berry to you. He's a mathematical physicist at the University of Bristol, where he has spent his whole career and is now Professor Emeritus of Physics. He has a BSc, a first degree in physics, from the University in Exeter, and a PhD from the University of St. Andrews. Is that right?
Yes,
St. Andrews.
that's right. Mm.
He is world famous for his many distinguished contributions to theoretical and mathematical physics, among which stand out first the very well-known Berry phase, a phenomenon observed in optics and quantum mechanics. His many contributions to semi-classical physics, which is nothing else than the borderland between quantum and classical physics, a very interesting and difficult subject. Quantum chaos in optics and other wave phenomena, such as the ripple scattered by a vortex in the surface of a water pool. The fine points in the mathematical theory of the rainbow, which is also very interesting mathematics and physics, and many others which would be too long to enumerate here. He has published over 400 research papers and many textbooks on different aspects of mathematical and theoretical physics. Sir Michael Berry was elected Fellow of the Royal Society in 1982 and knighted in 1996. He has received over 26 prizes and awards, among them the Dirac Medal and the Kapitsa Medal and the Polya Prize. From 2006, he has been editor of the Journal of Proceedings of the Royal Society. I'm not prepared, and you will not be happy if I enumerate his very long list of awards and prizes. He has a knack for uncovering dramatic and beautiful mathematical ideas in physical phenomena. So, Michael.
Thank you. I don't need it, I have this. Thank you. Well, thank you for this very generous introduction, and thank you for the honor of inviting me to share your celebration, because I understand you have been in existence, this Physics Institute, for 75 years. Well, that's a great honor. And it's also a pleasure, as all my visits to Mexico have been. It's really very nice that you invite me here. I'm working this week in Cuernavaca, but I have come here for the day. I'm going to speak about a subject which may be a little bit unusual to many of you. It's a subject on the borderland between mathematics and physics, as indeed was mentioned just now by Alfonso. And it has deep historical roots, and it continues to be developed today. And I will give you this long-term picture in my talk now. It's fundamentally a mathematical subject, but as I said, its development has been intimately related to physics, and it continues to be useful. And indeed the way of thinking that enables the mathematics to be developed is very much physicists' ways of thinking. So this is about divergent series. Let me start. Infinite series are the basis for many approximations in physics. You know, when I speak to people who are not physicists, they are surprised that we don't calculate everything exactly. In fact, we almost never calculate things exactly. We use approximations. And one of the commonest approximations is the infinite series. You make a guess, you improve the guess, you improve and improve and improve. Okay. Now, most series, however, are divergent. The convergent series that we learn in our elementary mathematics classes are exceptional and actually not very interesting. So divergent series are the norm in physics for reasons I will explain. Now, they're also the deepest area of asymptotics, the study of limits. And limits in physics are usually singular. And that's the reason why series diverge. And more philosophically, these singular limits lie at the heart of relations between descriptions of the world within physics at different levels. You know, quantum and classical, ray optics, polarization optics, wave optics, quantum optics. There are these different levels and different theories at each level, of course not incompatible with each other, but related by complicated limiting processes. Now, this subject has been a thread running through several centuries, running through mathematics, and this is what I'm going to tell you about. And the subject has been reborn a number of times, including quite recently, as I'll explain at the end. Now, the first reference known to me about a series useful in science, which is divergent, I came upon by surprise, and it's by Thomas Bayes. Now, Thomas Bayes, you know from Bayes' theorem in statistics. It's now very popular. I don't know why it's so fashionable. I mean, for a physicist, it's always obvious. It means you have to know the ensemble before you can make sensible probabilistic calculations. But this is a completely different thing. In 1747, he wrote a letter, submitted it to the Royal Society. It was not published until 1763. That's a lot, not because of problems with referees, but I don't know why. But he had died in the meantime. So here's the letter, and he said, if the following observations do not seem to you to be too minute, I would esteem it a favour if you would please communicate them to the Royal Society. And then he says, it has been asserted by some eminent mathematicians, by some eminent mathematicians, that the sum of the logarithms of the numbers 1, 2, 3, 4, etc. up to z is equal to something. It's Stirling's formula, we all know it. Curiously, he has a quantity c. He says if c denotes the ratio of the circumference of a circle to its diameter, so it's 2 pi, of course, we would call it. And he says that this is often quite accurate and useful, but he's puzzled by something. But the whole series can never properly express any quantity at all, because after the 5th term, the coefficients begin to increase, and they afterwards increase at a greater rate than what can be compensated by the increase of the powers of z, though z represent a number ever so large. So he realizes that Stirling's formula for the factorial function, here it is, Stirling's formula, some stuff and then a series, diverges factorially. There's a factorial here which will always beat any power of z, however large it is, and the coefficients then begin to increase, and he's puzzled by this. He can't understand how such a series can have any meaning. Okay. Now, between the submission of this paper and the publication of this paper, Euler wrote a series of much deeper, much more extensive investigations into divergent series, and he took them very seriously indeed as coded representations of functions. That's the modern view, which I'll describe in more and more depth as we proceed. It's not nonsense. There's a reason why series diverge, and it's useful to know that they diverge, and it's informative. But this view was not actually popular for a long time. Euler was ahead of his time. So, for example, Abel wrote, "Divergent series are the invention of the devil, and it's shameful to base on them any demonstration whatever." And then there are silly jokes about divergent series, allegedly written on the wall of a bathroom in Princeton University, 2 + 2 = 5, for sufficiently large values of 2. Okay. Well, the next major development was in 1838, and it was when Airy was giving the theory of diffraction near a rainbow. Now, this was fundamental physics at the time, because 30 years before, 40 years almost, Thomas Young had taught us that light is a wave phenomenon. So the description in terms of rays, which we of course learned from Newton and all previous people, Descartes and others, is only an approximation. And the most interesting features of waves are of rays are when they come to a focus on what are called caustics. And the most familiar caustic in common experience is the rainbow. It's directional focusing of light emitted from a raindrop. And Airy realized that there was a problem in understanding what waves look like near these very intense curves and surfaces. It's a curve here, the rainbow, because the colors is a separate thing. It was fundamental physics of the time how the old theory is related to the new theory near its singularities. And he realized, he invented the Airy function. It's an integral. This is the rainbow crossing variable, is z, and it's an integral which we nowadays, it's a standard function in mathematical software, but for him it was rather difficult to calculate, and here it is. In fact, he could only calculate this part, this little region, numerically. He did this because there's a convergent series for this function, which is hopeless outside this range, although it does converge, but it's useless numerically. And this was frustrating to him, because already in laboratory experiments, 30 of these interference fringes had been measured. And without having a proper way to calculate his integral, it was impossible to compare his theory with the experiment. And so it was very frustrating. This is a common thread running through science, the need to do numerical experiments when you can't calculate things accurately. I mean, there's, exactly. By the way, Descartes' theory in which he understood why light is concentrated at the rainbow angle, we now use trigonometry. We use Snell's law, and we calculate the bending and the refraction and the reflection and the distribution of the rays that emerge, and we can calculate where this rainbow angle caustic is. But he couldn't do that. He didn't have the facility with trigonometry that we have, and so Descartes did a numerical experiment. He plotted the paths of several tens of rays, and he saw that they were concentrated. It was very interesting. Now, of course, we've got lattice gauge theory calculations in field theory. You can't do them exactly. You do big numerical computations. Well, this was one. Okay. Now, but that was not satisfactory. It was Stokes who realized 10 years later that what was missing, I go back actually, what was missing was a theory for large values of Z, positive and negative. In other words, asymptotic formulas. Now, he found an asymptotic formula on the dark side. I'm writing it in a rather curious way. On the dark side, it decays exponentially. It's an evanescent wave. There are no real rays there, but there is an evanescent wave tunneling through, as we would now say. It was the first example. This is something negative. There's a reason for calling it F, I'll tell you later, multiplied by a series. And this series diverges factorially. So again, you have a divergent series. By the way, in deriving this formula and a similar formula on the bright side where you have oscillations, he did some very original things. Excuse me, sorry, I went ahead of myself. I want to just show you the divergence. These are the these are the terms for a particular value of f, it's a 15 or 20 or so, and the terms get smaller and smaller, but then they diverge. And they diverge where at the order equal to this quantity here in the exponent, this f. But he, in obtaining these formulas, he pre-invented what later was called the WKB method. That's on the dark side. On the bright side, he pre-invented what we call now the method of stationary phase. Very original person, non-rigorous physicist way of thinking, but extremely precise. You know, mathematicians say that they rigorously exactly prove the error bounds of certain approximations which are not very good. We physicists have extremely good approximations, but we can't calculate precisely how good they are. It's a common cultural interesting difference. Well, but Stokes was a very deep person. Anybody would, I think, be satisfied with what I've just described. But he was not, because he realized that there was a problem. And I call it the puzzle of the exponentials. You see, here's the area function. On this side, there's one exponential. Call it E1. On the other side, you've got two exponentials, which add together to give these oscillations. These are complex exponentials, the real exponential. Here they are, E1 and E2. Now one of them, E1, continues across to the other side. But where does E2 come from? And he was very puzzled by this, that the same function could require different exponentials with their series attached to them in different domains. This is now called Stokes's phenomenon. He identified it. And he discovered that what actually happens is if you go in a complex plane around, from the dark side to the bright side, dark side, bright side, he discovered that at 120 degrees is where this second exponential appears. Now there's a significance to that particular line. It's one exponential and two. The significance of the line is that on this line, this f is positive real. The function is exponentially large on that line. It's very small here, and it's oscillatory here. But here, it's very large. As I say, this is called Stokes phenomenon. This is now called a Stokes line. Well, what's the significance? The significance is that the second exponential is born where it's maximally dominated by the one that's already there. So it kind of slips in almost unnoticed when it's exponentially small. And that was Stokes's discovery. As I say, it's a very deep thing. Now, he tested it numerically. And I want to just run through his numerical test to show you how it works. Particular value, area function, z equals about 4. F is 11, you need 11 terms before the series starts to diverge. So here again is Stokes, right? And he calculated the function here, first of all. And he calculated it exactly using this very inconvenient convergent series. It really was a difficult task, but he did it. And then the series for the first exponential down to its smallest term gives you 6-digit accuracy. Then he said, let's look on the other side here. Let's look at this place. Well, here again you calculate exactly, and now the series for E1 is not so accurate. It's only 3-digit accuracy. So something is missing. But if you now add the small exponential, which he had shown would appear there, you add the small exponential, once again you get the 6-digit accuracy. So it really matters. Now, of course, once you get round to the bright side, these two exponentials have the same modular. They're both of order 1, but they oscillate, and their phase difference means that they interfere with each other. So that was his discovery. And it's the quietly beating heart of asymptotics, this Stokes phenomenon. The sudden appearance of a small exponential while hidden behind a large one, going from dark to bright, around the rainbow, if you like, in the complex plane, without passing through the origin. Now, this occurs throughout asymptotics. It occurs in integrals, in differential equations, integral equations, difference equations, series, and also more general types of caustics, focusing in optics, which I'll now describe. You see, here's a focused pattern. If I would be allowed to bring a laser on the aeroplane, laser bright laser pointer, which I'm not, and I only travel with hand luggage, I would do this experiment in front of you. But you take a laser, and a green laser, and a nice piece of bathroom window glass. No, wait. I'm not, of course, I could have borrowed one. A piece of bathroom window glass of the type that has random undulations, smooth undulations on the scale of the width of the laser beam, which is 1 millimeter or so. Well, you shine it, and then, of course, it illuminates the screen, and what you see is different rays in the laser beam hit different parts of the landscape of the glass and get bent differently and hit the screen in different places. And where you have more than one ray, you get interference, and the borders between regions reached by a different number of rays are the caustics. Now, the fold caustic is the name given to the kind that Airy was concerned with, the smooth curve. And these interferences you can see actually in rainbows about a third of the time. If you need meteorological conditions where the raindrops are comparable in size and they fall, and then you see one or two of these fringes. Of course, they're complicated by the fact that the colours are separated. Otherwise, when you don't see these fringes, they're obliterated by decoherence caused by the finite size of the sun or by the different sizes of different raindrops. But about a third of the time you can see one or two of these fringes. Okay, but then there's other kinds of signal. For example, the cusp caustic. And that's another integral. It depends on two variables, x and y. There it is, there's a cusp. And you can calculate the wave intensity there, color-coded here from black to red, red being bright. Okay, so that's another example of a caustic. Now, we're talking about Stokes phenomenon. Now, in the case of the Airy function, the Stokes phenomenon occurs in the complex plane. The caustic is this point, and these lines in the complex plane, both of them, I already showed you one, are where this small exponential appears. But for higher types of caustic, you can get the Stokes phenomenon for real variables. And I'll just show you how it works. Here's the cusp diffraction. Here's the caustic. Here's the caustic. It's called the bifurcation set. There's a technical reason I'll tell you in a minute. And here you have three real rays outside, one real ray and one complex ray. But across this Stokes set curve, one of the complex rays is extremely weak and disappears. You're left with just one real. And more generally, I mean, if you look at higher singularities, they have names. It's not the subject of this lecture to describe them, but grey are the shapes of the caustics in three-dimensional space, the focusing surfaces, and these coloured things sprouting from them are the Stokes set. So it's a general concept, this notion that Stokes was the first to encounter. I want to make a comment about Stokes. He was about to get married when he did this work, and he found it extremely difficult to understand, to get to the very heart of the Stokes phenomenon, as I will explain in a minute what his argument was. And he wrote a letter to his fiancée, a 55-page letter full of anxiety. Wow, should I marry? I'm worried about this. And then he said, in the last few days, I was doing something which I guess you won't let me do once we are married, staying up till 3 o'clock in the morning working hard on a mathematical problem. And then he says, I had this difficulty of Airy, which I thought about for many years, and in the last few days, after a very long fight, I finally mastered it. Now, you might think that his fiancée would not understand a statement of that kind, but she was the daughter of the Astronomer Royal of Northern Ireland, so she was accustomed to the peculiar ways of scientists. Anyway, that was Stokes. Now, just a little bit of mathematics. These are two contrasting phenomena, caustics and Stokes sets. And if you have an integral with some exponents, depending on some variable t, phase phi, then a bifurcation, the caustic, is where saddle points, where the gradients of the derivatives 2 points coincide, and so it's derivative vanishes to a higher order. And this is the violent birth or death of real waves. It's extremely large as you cross the caustic. That's why they're interesting, because the light's bright there. So two real waves one side, one evanescent wave on the other side. What's different with a Stokes phenomenon, Stokes set, is that there an evanescent wave disappears in the presence of a dominant wave, or appears. And that's a non-local bifurcation at two different places where the real part of these phases vanishes, difference vanishes. That means that the imaginary part of the phase, which is the real part of the exponents, are maximally different from each other. It's another way to speak about dominance. So it's a gentle thing, almost undetected, this birth and death of evanescent waves. There's a little caveat, but I won't go into it. Now, here was his argument. He argued that if you have a divergent series of this type, going to a small term and then rising, that this small term represents an irremovable vagueness in the way you can use it to represent the function. We know now that's not right, but that was his idea. Is an irremovable vagueness in a series truncated at its least term. And a small exponential can enter only when it's smaller than that irreducible vagueness. And he did a calculation, and that only occurs in a very narrow domain around the Stokes line. So that was his argument. It's a good argument, but it's not, we can do better. We understand now that this second exponential is born out of the resummed tail, the divergent tail of the series, by a universal mechanism. So you have one series to the least term, then you look at the divergent part of this tail and you manipulate, do things with it, and it gives rise to this second exponential, as I will explain. And this f is this natural large variable. It's the difference between the exponents. And the least term is the term of order of f. Asymptotics, well, let's say we have a series, some coefficients divided by nth power. You stop at the least term, but then that's the main part, the head of the series, and the rest is the tail. Now, we want to know what that tail is like, and for that we need the asymptotics of the asymptotics. That's large N. Asymptotics is far away from the caustic, large F. But you have an infinite series, and you want to know what its high orders are. And here we have something which begins to the modern era. There's a universality in the behavior of the high orders of divergent series of this type. It wasn't obvious at all. It goes back to an idea of Darboux, and here's Dingle. He was my PhD supervisor, and I learned about this work from him, but I never really appreciated it until almost 30 years later. And this is Darboux, and it's this, that the tail, huge variety of series, very different coefficients, is like a factorial divided by a power, as in the examples I've shown you. Now, why should this be so? I'll tell you why it's so in an intuitive way. All of these approximations, successive terms, are in a sense local approximations. So in WKB, in quantum mechanics, you expand the potential about a particular place. In the stationary phase, you expand the exponents around the saddle point. And that means that the higher terms involve higher and higher derivatives of something. Now, it's a theorem of Darboux that very high derivatives of any function, analytic function, are determined by the nearest singularity. So the more derivatives you take, the more that singularity becomes dominant. And if it's a branch point or a pole, which is the common case, you differentiate that many times, you just get a factorial. That's where it comes from. But it's universal, and it's a huge simplification. Anyone who's worked with real divergent series in a real application, not the standard illustrative examples, knows that very quickly the terms get incredibly complicated. I just want to show you the 20th term of a series that's implicated in the theory of the Riemann zeta function of number theory. So there it is. That's the 20th term, and it involves a function itself whose derivatives are involved, as well as these horrible coefficients. And here's the 60th derivative. So they really are complicated. And to know that when you go to high numbers like 20. All of this is well approximated by a factor, is a huge simplification, and it enables you to start to deal with these tails seriously. So now what's that? It's the asymptotics of the asymptotics of the asymptotics. You calculate the tail, which is already from an asymptotic series for large f, but for large n, but you want to calculate it for large f. Okay, and well, you can use something called Borel summation. I don't want to go into that. It gives you an integral representation of the tail. There's a formal trick that stops that being divergent. It's an illegitimate mathematical procedure, undoing an illegitimate mathematical procedure which made the series diverge in the first place. I won't go into that, but what you get is the following. It's an approximation of what happens when you cross a Stokes line. I've now tidied things up. Stokes phenomenon occur in this plane of f. F is real, is the Stokes line, and so when you cross it, you go, the imaginary part changes sign. Okay? So that's where you have to evaluate this, and it's born not suddenly, but smoothly, but in a very narrow zone, according to a universal scaling law in terms of an error function. Now, I want to show you that. I'll show you it for the area function. You take the area function and you scale it a bit, and you subtract off the dominant series down to the least term. Now, that's something big, near the Stokes line. Area function is big, so the approximation is big as well, the exponential is big, but the difference is quite small, and you multiply again by something big, which is the large exponential, and then you get something, the difference is of order 1. That's the scaling you do, and you can do this for any divergent series, not just airy, and then what you get is the following. You have a natural variable, the imaginary part of f, that's the rainbow, that's the Stokes line crossing variable, divided by the square root of twice the real part. That's a large thing, so this is small, this scaling quantity, here it is, I've shown you, you're crossing the Stokes line, there you are, in terms of angle, and sorry, I didn't say, and this is an error function of this variable, excuse me, this is the theorem, this is the result. So how does it work? Well, let's just look. I've given you 2 examples here of the tail. One of them is for f equals 3, the other is for f equals 10, which then should be sharper as it is, and this is in degrees, you're crossing the Stokes line, and well, this goes from 0 to 1, this tail, sharper when f is larger because of the behavior of this variable. Well, just to show you, this is the exact, and here's the approximate theory, and you see that it works very well. You really have achieved what you aim, which is a precise description of how this Stokes phenomenon occurs. This quantity isn't exactly real. In a limit it's real, but as you see, the imaginary parts here are rather small. Just to show you, the disparity for this case of the 2 exponentials is about 22,000. You subtract off 22,000, multiply by something big, and you get something of order 1. So you really are getting deep into the details of a function using this asymptotics. Okay, and this is the error function in the area function. Okay, now there are many applications in mathematics to approximations of a variety of functions. The error function in Bessel functions, hypergeometric functions, gamma functions, even the error function itself. More generally, integrals with coalescing saddles, the Riemann zeta function is hugely general phenomenon happening in this way. And there are physical applications to the reflection of waves by refractive index gradients, and the histories of quantum jumps, I'll talk about that in a minute, induced by slowly changing external forces, particle pair creation, breakdown of slow manifold, I don't want to go into this, in systems where you have fast and slow variables coupled. I'll just show you something about histories of quantum jumps. Imagine you have, as you often have, a quantum system acted on in an eigenstate of some Hamiltonian, which you then slowly change to some other value. Well, if you change it slowly, there's an adiabatic theorem. You'll stay in the same state. But you won't stay exactly in the same state. You will make a weak transition to other states, let's say there are just 2, to the other one, which is exponentially weak in the slowness parameter. That's long known, very familiar. What was less familiar is the history of this transition. How does it actually happen that you go from 0 occupancy in the excited state to this exponentially small occupancy? Well, I want to show you that. Transition probability as a function of time. And I want to show you these series of pictures are using slightly different bases corresponding to different levels of approximation of your evolving state to the instantaneous eigenstates of the system that you're interested in. And the final probability is exponentially small in every case. Well, here's the lowest order. Well, then you see you get from 0 to exponentially small via a series of oscillations. You see and these oscillations, they're small in terms of 1, they're actually of order square root of epsilon, but they're enormous compared to the final result. These two curves are two different Hamiltonians. It's to show the universality. But as you go to higher and higher bases, until in the end you get to when the series will start to diverge, you see this error function very nicely emerging. There are a few little wiggles. They would go away if I chose a smaller value of epsilon. So large oscillations en route, getting smaller as you approach the optimal order. In this case, it's n equals 5. So this is an illustration. How quantum jumps happen depends on the basis you use to describe the evolving quantum state. But if you use an optimal basis, then you get smoothly from the initial to the final exponentially small transition without any huge oscillations. So that's one comment. Now, I'm embarrassed by this. I wrote a poem. Excuse me. You'll forgive me. I'm going to embarrass myself and probably you about the story so far. I called it emotional asymptotics. Okay. Passions rise. We cross the bifurcation. Something intense and complex is born. But it is evanescent from the start and soon decays. Much later, we meet again. Now there's another dominant exponential in her life. As we cross our Stokes line, all passion vanishes. The whole thing was an error function. Okay. Now, you see, in mathematics, they commonly use a definition of an asymptotic series due to Henri Poincaré. Now, he was an utterly brilliant mathematician, immensely creative, but I think this was a mistaken step because he defined an asymptotic series by what's left over if you stop at the nth term where n is fixed. Now, that can't capture exponentially small terms because the n has to be linked to the large variable or the small parameter or whatever it is. Moreover, it doesn't distinguish divergent series from convergent ones. So Poincaré's definition of an asymptotic series essentially held the subject back for a long time because Stokes, 40 years before, had realized that you have to go further than a given order, like the third or the seventh. You have to go to an order which is of the order of the large parameter, but that got forgotten until it was revived more recently. Now, let's use the term superasymptotics, is summing to the least term. That's you go to the term of order r or n is equal to this f, and then you get the Stokes phenomenon and furthermore this smoothing of the discontinuity. Okay, now this captures small exponentials. Martin Kruskal had this nice phrase, asymptotics beyond all orders. Very nice expression. Now hyperasymptotics is to go beyond, and that's the story as it is today, and that's repeated resummation based on a principle called resurgence, which was discovered by Dingle, actually, very immensely deep insight, and then rediscovered but developed much more in a formal sense by the mathematician Jean Écale in the 1980s. So here was Dingle again, and here's Jean Écale. And the idea is this: you take very seriously this fact that series don't diverge for no reason. The divergence of a series must reflect its cause. Well, what is the cause? Why does that series on the dark side diverge? Because it's a series run by only one exponential, but really hidden away. There's another one which is going to appear, and you can't, with a convergent series of one exponential, capture the second one. So the divergent series is telling you something. Okay, the series multiplying each exponential must diverge in order to accommodate the other exponentials. There can be more than two. I mean, there can be any number, depending on the problem. Now, moreover, each component series must contain, coded into its high orders, information about all the other exponentials and all the terms of the series that multiply them. So, taking seriously this fact that series are coded representations of functions, these high orders of all the different exponentials must be beautifully related to each other. And how they're related are what's called resurgence relations. I'll show you one. The simplest case, where there are just the two exponentials, half f and minus half f, so the difference is f. Okay, so here's a series, here's the high orders. Now, I already told you that the high orders diverge factorially, but that's just the first term of the behavior of the high orders. You then get a series of corrections, and each of these corrections, one by one, involves the coefficients of the original series. So that's a very beautiful thing, and extremely powerful, and it's in principle exact. Now, this is what hyperasymptotics does. You have some series f, and you want to sum it. Well, you get a series of series. The primitive asymptotics, you just include A0. And by the way, for many purposes, that's good enough. I mean, the leading order behavior is very accurate. For many years, as a physicist, I proudly called myself a first terms man. Okay, and the point being that if you have the first term sufficiently subtle, and if you have coalescing saddle points, you need more complicated series, complicated expressions, not just an exponential, you get extremely accurate results. But then, much later, when I started to understand the Stokes phenomenon, I realized this beautiful world of high orders of the series is indispensable. Okay, so then superasymptotics, where are we? Superasymptotics is you go to the least term of the series. Now, then you can get an integral expression for the remainder, which you can again find an asymptotic series times to its least term, called the S1. And so you go on, once again, each time you get a series, you go to its least term, and each time you do this, you get exponentially smaller every time. Now, Dingle had envisaged this scheme, and he did some preliminary computations for the first stage of it, but Chris Howells and I in the 1990s took it very seriously and then used it. You can, with computer algebra, you can go a lot further than he was able to do, and you can actually see how this works. And I want to show how it works, first of all, the Airy function at this value of z, f equals 16. You need all these numbers, right, 5. So here we are. Now, this is the 0th stage. That's the first term. The error is of order 10 to the minus 2 or 3 or so. And then here's superasymptotics. The error is about e to the minus 8 or so, 10 to the minus 8. And the first stage, the second stage, the third stage. What happens is that it's a kind of renormalization. These hyperseries get smaller and smaller, and then they stop. When they stop, the series isn't exact. There are the result, but it's much smaller. It's about, instead of e to the minus f, it's about e to the minus 3f. It's very much smaller. There are variants of the scheme where you can get infinite accuracy, but they involve going beyond the least term and involve having exponentially large terms which then cancel off. I won't want to discuss that. So it's very accurate, and here we are, the 4th stage. And now you've gone down to 10 to the minus 18, which is why I needed all these numbers. Okay. So as I said, the optimally truncated hyperseries gets shorter. Now, when you've got more than 2 exponentials, there's a graph structure of the higher approximants. Imagine you have an integral with a number of saddles. This is the plane through which your path of integration passes, and you have a series of saddle points, which I've indicated here, which in principle would give contributions. But imagine your path goes through one of them, just this one, let's say, a basic saddle. Then at the next level of hyperasymptotics, you bring in adjacent saddles, and these are ones reached by a topological criterion. You let the phase of this f vary, you take the steepest ascent path, and you'll hit certain saddles. The ones that you hit are the ones that must come in at the next stage. Well, when you go again, you hit the ones which are even further out, and so on. You keep going, kind of multiple scattering series. I want to illustrate how this works. For Pearcey integrals, my last technical thing I'm going to show you. Well, here it is. You have 2 variables here. This is an integral. Take x equals 7 and y is 1 plus I. Nice typical case. It's quartic, so there are 3 saddle points. Here they are, 1, 2 and 3. Here's your path of integration going through. Now hyperasymptotics generates a sequence of series from multiple scattering between these saddles, and I just want to show how that works. You've got, first of all, the basic series, superasymptotics. Then you go one scattering, you have 2 series from path 2 to 1, 2 to 3. Then 2 scattering, so there's only 1 series, 2 to 1 to 2. 3 scatterings, there's 2, 1, 2, 1, etc. So different multiple scatterings occur. And how does that work? Well, the lowest level is accurate 10 to the minus 2. Superasymptotics is 10 to the minus 4. And the ultimate hyperasymptotic is 10 to the minus 12. And then, of course, you've got the exact, which we compute numerically with some difficulty. And so each time you improve, look how you improve the number of terms, the number of digits of accuracy that you get. So this is a very powerful scheme, which you couldn't implement until you had computers to do a lot of the algebra that's involved calculating the terms, which are very complicated. I want to honour 3 people, because in the last few years, 3 leading asymptotists of the late 20th century have died, and I wanted to talk about them. One was, as I mentioned, Dingle, and he really had this very deep idea that divergent series have universality, to use a physicist's term, in their high orders, and you could use this to get this form of resummation based on the resurgence. The higher orders of a given series encode the lower orders of all the other series. Then there's Frank Olver. Now here he is holding the Abramowitz and Stegun's Handbook of Special Functions, which he, in the 1960s, was one of the contributors to. He wrote the chapter on Bessel functions. You know, all of us as theoretical physicists know this book. I wore out 3 copies in my career as a physicist of this book. And the last thing he did in his life, very great thing, he was supervising as the editor-in-chief of the digital library of mathematical functions, which is this on the web. Some of you may know, if you Google DLMF, digital library, you'll find a much expanded version with all the formulas for asymptotics and so on. And asymptotics for special functions was his forte. It's a very valuable resource. In fact, once you find this website, you will never use this book again because it's so easy to click and everything is hyperlinked and so on. And finally, there's Martin Kruskal. And he coined this phrase, asymptotics beyond all orders, and his contribution was to apply what is a rather simple notion of exponential asymptotics compared to what I've been telling you, but to nonlinear equations where new ideas come in there. And he also, in the later part of his life, had an idea which I didn't follow, but he wanted to understand asymptotic series as rigorous objects using surreal numbers as defined by John Conway. I didn't quite follow him there, but he made many brilliant contributions. He encountered divergent series in the study of adiabatic invariance, which he needed in the early days of plasma physics, when people were beginning to think of confined plasmas for confined thermonuclear reactions. And so that was how he encountered this divergent series. And then finally, not quite finally, a kind of joke, it was pointed out to me by Chris Howells. Chris Howells was my student and my colleague with whom we devised the hyperasymptotics and worked it out in detail, that a surprising number of asymptotics-related people came from the same area in southeast London. It's a strange thing. So here's Airy, who was the Astronomer Royal in Greenwich. Here's Pearcey. The Pearcey function is diffraction near a cusp. He was born in Woolwich, which is near there. And Frank Olver himself was born a little way away in South London, Croydon. Again, and Chris Howells himself comes from Greenwich. I come from a slightly different, slightly farther away place, but also London. Curious thing. Okay, now, what's the legacy from all of this? From Euler, from Dingle, from École, from Thomas Bayes' puzzlement at finding this divergent series. You have to remember, Thomas Bayes was working completely alone. He was a country priest in a little church in Kent, just thinking quietly by himself, not really talking to many people, but discovered this rather surprising thing. Anyway, Stokes insisted, on understanding how the rainbow's dark side is connected to the interference fringes on the bright side. And what came from all of that, and Euler, Dingle and Écault, was this: a divergent series is not meaningless, nor is it a nuisance, but it's an essential and informative coded representation of a function. Now, in the 1990s and in the 2000s, much new mathematics was developed following upon these ideas that I've described to you, different names of people here. Now in the 2010s, this subject, to my surprise, has come to life again because in field theory and string theory, there are immense mathematical difficulties, and people begin to realize that some of the divergent series you get, you can understand them using these ideas of resurgence and Stokes phenomenon and the like. And there are a number of papers by the string theorists, resurgence theory, decoding perturbation theory, using Stokes phenomena, saddle points and so on, and very sophisticated ideas are being developed. These are frighteningly clever people, I must say, as I discovered because a few weeks ago I was at CERN where there was a conference on precisely these subjects. It's been reborn yet again in this area. I want to make a comment. When I was a student in the 1960s with Dingle, he said that one of his motivations in developing these ideas in asymptotics was because of the divergences of quantum field theory and quantum electrodynamics and the like. He never made those applications, but now they are being made. I want to say finally, I regard this as as a series of little steps in humanity's long study to understand infinity. You know, it's easy to forget how surprising a convergent series is. We know it, you learn it, but it took thousands of years for people to know that you can add up an infinite number of numbers and get something finite. You know, this is the resolution of one of Zeno's paradoxes. You know, Zeno was puzzled. How could he ever walk from one place to the next? Because going from here to here, he has to cover half the distance. Well, you still have to cover half the distance. And you still have to cover half the distance. And of course, he didn't, I suppose, spend his life standing still, but he realized there was a conceptual problem. And it was thousands of years before people realized that that's a convergent series. Well, that was one step in understanding infinity. And Cantor, of course, with his different orders of infinity from set theory was another. And in a small way, all of this, what I've told you today, is again a little step towards understanding, grasping, groping towards understanding infinity. So thank you very much for your attention.
Thank you very much for this nice talk, and we have time for some questions.
So you mentioned that this is universal, that many asymptotic series, the coefficient grow factorially.
Yes, that's the point. You can easily write down ones that don't, but the ones that occur in physics, that are solutions of differential equations or integrals, for this reason I gave, because
Saddle point.
yeah, but that's right, and it's for the reason I said, which is that they're all in some sense local expansions, and so the higher terms involve higher derivatives, and derivatives of a function almost always diverge factorially because of this theorem that they're dominated by the nearest singularity in the to the place where we evaluate. In the beginning, first few derivatives, you don't see the singularity, but the domain spreads and spreads. In the end, this singularity dominates the derivatives. There are many amusing conclusions of that. I wrote a paper a few years ago, make this point. If you take almost any function that's analytic in a strip, and you differentiate it more and more times, it almost all functions become cos x. I mean, scale x, scaling of cos, but it's again a consequence of this. It's a strange thing which should be in textbooks, but it isn't. There's a universality in repeated derivatives, okay, and that underlies the behavior of all these asymptotics. Okay, yeah.
Yes, the problem for example, in electrodynamics,
Yes.
that kind of theories, is that you don't know the exact solution.
Indeed.
That means that you don't know the singularities in
You
the sense that
true.
you're explaining.
Yes, indeed.
So how would
Indeed.
use
Indeed. Well, absolutely. Well, for example, sometimes you can identify by if you can calculate high terms, you can see the factorial divergence, and you can find this f, because factorial divided by power, you can find what the power is numerically, and this is often a clue to telling you what the small exponential is. I'll give you an example. In the Riemann zeta function, there's something called the Riemann-Siegel formula. Never mind what it is. You have the Riemann zeta function is interesting on a certain line in the complex plane. You want to be very high up this line, and this Riemann zeta is extremely complicated. However, you can calculate the high orders of the series. It took me almost a year to do it, and then this then tells me what the f is, and tells me what the small exponential is, and that gives a clue to the physics underlying this Riemann zeta function. It tells you there's a small exponential hidden away, and it tells you what it is. So there are different ways you can use it. Of course it's a problem, and in real problems you often don't know what you say is quite right. In the string theory applications this is certainly true, but again people are looking at different models for all the different diagrams that you can sum, and understanding the what small exponentials might be and what they would mean. They're called false vacua in the theory. So they're using in a constructive way these ideas precisely in the situations you describe where you don't know. They're the interesting cases. You know, Feynman in his Nobel lecture, there's hidden away a tiny little remark, because he showed how the fine structure constant makes the successive terms of in quantum electronics get smaller and smaller. It's 1 over 137. He says, I have a feeling that if ever we could calculate this to the 137th term, we would see something interesting. And what he means, of course, I don't know how much he understood, but he glimpsed that the series would start to diverge then.
Has anybody calculated?
No, of course not. Of course not. No.
Sometimes when one is summing integral numbers, one can use reflection formulas that lead to zeta function.
Absolutely.
Yes, could it be somehow related with this?
Very much so. Very much so. And indeed, in the what's it called? In the Riemann zeta function, it's called the functional equation, which relates in the gamma function. You've got all various symmetry relations. Now, what I didn't tell you, but I just mentioned it on a slide but didn't speak about it, was that what the Stokes phenomenon tells you is actually not that a small exponential is born, but that one that might be already there will change its strength. Now, if it's not there, then it is born with a certain. It tells you how the coefficient changes. So how do you know from asymptotics how much of a small exponential you have to begin with? The answer is you use properties you know, like reflection formulas or whether a function is real on the real axis, things of this kind. So such, I didn't say this, but such relations are incorporated, and actually they can be expressed to higher and higher order and built into the asymptotics in practical ways. So is what Andrei Voros does this extremely beautifully in what he calls exact WKB method. It's essentially this type of study, but taking full account of various reflections and symmetries that you have, depending on the potential, in his case, that you're looking at. So thank you for that question.
Another question? Sometimes when you see expressions for the conductivity or resistivity, you find a Dingle factor, something that is called
Dingle is the same Dingle.
Does it come
Now,
from
yes, I'll tell you. Now, Dingle in the 50s had a successful career as a condensed matter theorist, solid state, as it was then called. And there's a Dingle temperature, there's Dingle-Holstein resonance, there's a Dingle representation for the states of a particle in a constant magnetic field, a different way of dealing with the infinite degeneracy from the Landau solutions that we know. There's the racetrack orbits. So he did many things, and it was in the course of that work that he found certain Fermi-Dirac integrals which needed to be evaluated to exponential accuracy to capture physical phenomena. And that's what started him working on asymptotics.
Okay.
Precisely problems he encountered from certain integrals in solid state physics. Yeah.
Okay. Ruben?
Yeah, about the physics of the rainbow.
Yes.
This is one way of looking at the interference between the bright side and
Yes.
the dark side. But it's in another way of looking at the same problem that will give you the same understanding of the physics behind the rainbow? Or not?
Well, I mean, of course, you can solve exactly the electrodynamics of a plane wave from the sun encountering a dielectric sphere. And this was done by Gustav Mie, M-I-E. It's the Mie theory. You get a series of spherical circular harmonics and with phase shifts and so on. Now, the problem with that is that it's exact. Of course it is. But in order to get from that to a comprehensive physical understanding, you need to use approximations, and it's only for large values of the radius divided by the wavelength, large spheres, that you see the rainbow, because otherwise you just see a blur. And interesting, you can calculate it. Now, Moises Nussensweig wrote extremely beautiful papers in the 1960s using this approach. And I also did some work on the analogous quantum scattering problem, resumming the phase shift series, multiple different angular momentum series. The basic tool is the Poisson summation formula, where you take a series over eigenvalues, which is this partial wave series, and it converts it into a series that represent different topologies of rays. Now, so yes, of course, that's correct, but it's a very good example of how you can have a deeper theory in physics, but it often doesn't explain in a simple way in principle it works, but it doesn't explain which geometrical optics does with Descartes and its successive improvements. I'll tell you a story about that. There's a novel about this phenomenon that you can have a theory of everything, but it's hard to use it to explain any particular thing. It's in a novel by Ian McEwan, and in this novel is a badly behaved string theorist whose wife catches him in a situation with another lady, and he says, "Don't worry, my dear, I can explain everything."
All this is related to renormalization, isn't it?
Well, I mean, yes and no. I mean, renormalization, this is perturbation. It's writing a series of correction terms. Renormalization is an iterative process. Now, it turns out that you can express some of these asymptotics, WKB theory, in terms of iteration rather than perturbation. But still, the iteration diverges at roughly the same place. And in the end, I was actually quite surprised to discover this in the 1990s. In the end, there's not much difference between the two approaches. Now, of course, there are other subjects there are. I mean, critical phenomena, renormalization is fundamental. I mean, iteration is very much superior to perturbation, but that's not always the case. So there are connections, and they're similar, and they're sometimes separate. Yeah.
One more question? Well, if not, we thank again Professor Emérito.
Thank you.